Hi, welcome to another session for heat transfer subject. In this session, we are going to talk about heat conduction equation. In previous sessions, I told you about the heat transfer, and we have seen the three modes of heat transfer: conduction, convection, and radiation. And we also have seen some basic equation to find it or to calculate the heat transfer value by a simple equations. Here we are going to more discuss about some equations for the heat transfer, especially heat transfer by conduction. So let's see how we can develop appropriate equation to find the heat transfer value to determine the temperature in the for the medium or for the object which we have heat transfer through that. But before that, we need to understand what is the differences between the temperature and heat transfer and to be able to develop appropriate equation. First of all, however, in heat transfer, we are mainly dealing with the temperature and temperature in different point of the medium, which we have heat transfer in that. But there is a big difference between the temperature and heat transfer actually. Temperature is a scalar quantity. In other words, we just need a value which shows its magnitude. For example, 50 degrees Celsius. The temperature of this hot baked potato is 50 degrees Celsius. That's enough, and we know how much is the temperature. How about heat transfer? Heat transfer is a vector quantity. In other words, we need to have a value which shows its magnitude. For example, 80 watt per meter square. We know how much is the value or magnitude of the heat transfer, but in which direction? The direction of the heat transfer also is important. Because of that, we call the heat transfer as a vector quantity. It has magnitude and also the direction. The other example is the heat transfer through medium like this: hot medium, cold medium. And you know, we heat transfer is always from hot medium to the cold medium. So the direction is in this direction, and its value is 500 watts. So when we are dealing with the heat transfer problems, we need to understand, or we need to define or find the direction of the heat transfer as well. So we first we need to find or to decide about the coordinate system which we can use or we are going to use to develop appropriate equation for heat transfer by conduction. As you may recall from mathematics, we have mainly three different coordinate systems: rectangular coordinates, cylindrical coordinates, and spherical coordinate system. Imagine we are going to talk about the heat transfer and or the temperature in a medium at the point P, for example. So the temperature of this point P at this location is a function of the directions and also in other words the location of the point actually, and also the time. So in the rectangular, for example, coordinate system, temperature of point P is a function of its location: x, y, z. X this direction, y this direction, and z is direction. So how much is x, y, z for this P? Simply we can find its location and at which time. So in the rectangular uh, mm, coordinate system, simply by these four components we can find the temperature for a point, or temperature of point P is a function of x, y, z, and t. And this point at cylindrical coordinate system is a function of r, phi, this angle, and z, in this direction. So by r, phi, and z, we can find the location of the point P in this coordinate system, And also, again, the temperature of this point is a function of temperature as well. And for a spherical coordinate system, we have r, the radius from our reference to this point, and two different angles, phi, the angle between the r and x direction, and theta. And you may recall from mathematics, which we can find r, phi, theta by triangular equations and so on. But here in our calculation for heat transfer, mainly, uh, we use different coordinate system to simplify our calculation. So we usually don't need to calculate the r, phi, and or theta based on x, y, z. However, always we can calculate them, but usually we just use this three coordinate system based on the geometry of the object, which we are going to find to find heat transfer for that object. So based on the shape of the object or medium, we can use each one of these coordinate systems. So we know that the heat transfer is a vector quantity, magnitude, and direction, and also we can use three coordinate system to show the direction of the heat transfer. Next is the other important thing which we need to know about the heat transfer before we develop the equation is we may have a steady or transient heat transfer. We have a steady heat transfer when no change with time at any point of the medium. There is the condition of the heat transfer. For example, this is time 2 p.m., 5 p.m. We have heat transfer through this medium due to the temperature difference 15 degrees Celsius at this surface, 7 degrees Celsius temperature of this surface. So we have heat transfer in this direction. Okay, and at 5 p.m. again, temperature has still is 15 degrees Celsius, 7 degrees Celsius. So we have a still heat transfer in this direction. But the value of the heat transfer rate also is same because the temperature has not changed. Uh, each one of them are still same 15, 15, 7, 7 degrees Celsius. So Q dot 1 at 2 p.m. is equal to Q dot 2 at 5 p.m. But if we type, 2 p.m. here again, the temperature 15 degrees Celsius, 7 degrees Celsius, we have Q dot 1, the value, the direction of the heat transfer. At 5 p.m., temperature of this surface has reduced to 12 degrees Celsius, and temperature of this surface has reduced to 5 degrees Celsius. So it means Q dot 2, the heat transfer at this time is not equal to Q dot 2 heat transfer at 2 p.m. due to the change in the temperature of the object of these two surfaces with time. So in this case, we have transient heat transfer. Transient implies variation with time or time dependent. The heat transfer value or the heat transfer value is dependent of time here. In some special cases, when here you can see 15 and 7 degrees Celsius, they have reduced, they have changed actually. But in some special cases, in the variation with time, we have variation with time, but not with position. In other words, that is a special case that we will see in some examples in future, actually in the future chapters, especially the temperature of the medium change uniformly with time. Like imagine we have a ball of iron. Its temperature totally change with time, but the temperature, for example, for this whole object, the ball, which we have after 1 hour, for example, from 50 degrees Celsius is reduced to 40 degrees Celsius. So the temperature totally has changed with time, but the temperature in which each point is still same in whole body. In this case, we have heat transfer. We call this heat transfer system as lumped system. in future we will see example related to that. So up to here, we have understood some basics about the heat transfer. Now let's see. Uh, I told you that we have direction of the heat transfer, and in real world, we have always heat transfer in the three directions. We have three-dimensional, heat transfer, X, Y, Z. Then, in real world, we have three direction for displacement, for transfer, and so on. And heat transfer also can be uh, in those three directions, X, Y, Z always. But in some special cases, when the heat transfer in one direction or two direction is small compared to the other direction, then we can ignore them. So generally, we have three-dimensional heat transfer. In any object, the heat is transferred in X, Y, Z in all directions, all possible directions actually. But in some special cases, for example, the heat transfer in Y direction can be neglected, or it is very small, or it is zero. So we have only heat transfer in X and Z direction. We call that two-dimensional heat transfer. In some special cases, in two of these directions, the heat transfer is zero or is very small. It is not significant compared to the heat transfer in the third direction. So we can ignore the heat transfer in those two directions. In this case, we have one-dimensional heat transfer. Some examples of this 2D. As I told you, the 3D heat transfer, we have always 3D heat transfer, but in some special cases, we can simplify to two-dimensional and one-dimensional. One example of the two-dimensional heat transfer is in the rectangular bar, a long rectangular bar like what you can see here. Imagine we have, the heat transfer through this bar. Usually, the heat imagine, we have in this direction is the length of the bar is in this direction as it is shown here. Usually, the temperature through the uh, one in one direction of the bar or length of the bar remain constant, 80 degrees Celsius, 80 degrees. In the Z direction, temperature is constant. So we don't have heat transfer in this direction. How about the X and Y direction? In X, if you notice here is 80 degrees Celsius, here is 70 degrees Celsius. Higher temperature, lower temperature. So we have heat transfer in this direction. And about the other direction, Y. Here again, we have 80 degrees Celsius. Here is 70 degrees Celsius. Here is 65 degrees Celsius. So in this direction also we have heat transfer because we have temperature difference. So this is an example of two-dimensional heat transfer. An example for the one-dimensional heat transfer is the glass or the window of the house. We have heat transfer through the glass or through the window of the house, for example. So the heat transfer, in this case, again, we have a three-dimensional heat transfer, but the heat transfer through the edge, in this direction, just the thickness from that, for example, the area will be just a few millimeters compared to this, for example, 1 meter, 1000 millimeter. And this area, a big area. And for heat transfer, the area normal to the direction of the heat transfer is important. So in this direction and this direction, the area is very small. So heat transfer in these two direction is negligible, and only heat transfer in this direction because we have a big area is important. So in this case, we have a one-dimensional heat transfer problem. So you can see two examples of two-dimensional and one-dimensional heat transfer problem. This will help us a lot when we are dealing with real examples and when we are going to calculate heat transfer value by conduction for different medium and objects. And about conduction, because in this session we are mainly going to talk about the conduction. If you remember, we have this equation. This is an element, or this is a wall, for example. You know that we define the coordinate system like this: x and t. This is the direction. This is the t, or temperature. The higher temperature here is lower temperature. Then due to this temperature difference, we have the heat transfer in this direction. And you remember this equation for your law of heat conduction: q dot by conduction, or rate of heat transfer by conduction, is equal to negative k a times differential of t with respect to x, or direction. K is the thermal conductivity of the medium. A is the surface, the area normal to the direction of the heat transfer. Differential of temperature with respect to the x shows the temperature difference actually here. And usually, and it shows actually the slope of this, this graph, which shows the heat transfer, well, exact value, how the direction of the heat transfer actually. This slope, or actually the T2, T1, T2 minus T1, is usually negative, but we know the heat transfer is in this direction. So to have a positive value for Q dot, or rate of heat transfer, we add this negative sign here. I have already discussed about this in previous uh, chapter. So we just recall the Fourier law of heat conduction here for an element like this. Now, if you are going to develop this Fourier equation for a three-dimensional element, like what you can see here, here we have only x. Now we are going to see, if we have three-dimensional element, how will be the heat conduction through that element. We have three direction: x, y, z. So simply we know from this that we need to write the Fourier law for all of these directions, and for each one of them, the a, or area, it depends on the direction of the heat transfer: ax, az, ay. Q dot x is the rate of heat transfer in the x direction, q dot y, q dot z. So for this three-dimensional element, the general form of the equation for the to calculate or to find the rate of heat transfer is like this: q dot n is equal to negative k a partial of temperature with respect to n, which n actually the shows we have a three-dimensional heat transfer. In this case, q dot n will be equal to q dot xi. If you remember, we have resolved the q dot n to its component. Q dot n is in this direction. If we resolve it into its three uh, uh, components, it will be like this: q dot n equal to q dot x I plus q dot yj plus q dot zk. If you remember from mathematics, this is the procedure to resolve a vector to its components. And q dot x here is equal to negative k ax partial of temperature with respect to x. So k, here we imagine k remain constant for the element, or is same for in each direction. Ax, ay, az are the area normal to the direction of the heat transfer for x, y, and z. And the temperature difference should be considered for each direction. Here, partial of temperature with respect to x for q dot x, partial of temperature with respect to y for the heat transfer in y direction, and same for z direction. So we have this general equation to find the uh, rate of heat transfer through a three-dimensional element. However, we will see later that we will develop a more equation to exactly find the amount of the heat transfer by conduction. The other important thing when we are calculating the heat transfer for an object or medium is if the object also itself generate any heat or thermal energy or not. For example, when we have a hot wire, we are going to calculate heat transfer from the inner surface of the wire or from the center of the wire to its surface, for example. Then we have temperature difference between them. We can calculate heat transfer. So heat generation in the medium also is important. So, for example, like wire, when you know about that, when we have electricity current in the wire, due to the resistance in the wire against the current of electricity, we have heat generation in the wire. So we need to also consider and include that heat generation to find the, for example, temperature on the surface of the wire. So this is one example. The other example is fuel elements of nuclear reactors, which itself will generate the heat. And also the other example is exothermic chemical reaction. When we have a chemical reaction which may cause heat generation inside, something. Imagine we have a ball, we have temperature difference, from the we have a shell ball, actually a shell, then it's a shell, a sphere actually, then due to heat temperature difference, we have heat transfer through the wall of that shell, but also if sometimes we have heat generation inside the wall of that shell, so we need to consider that one as well. Anyway, so we have heat generation. We see some example here. For example, the absorption of solar radiation by water can be treated as heat generation. Here, for example, we are going to find the heat transfer through the water. We have temperature difference from this point to this point, so we have heat transfer. That's okay. We can calculate by the Fourier law the equation. But also when the sun is, due to radiation of the sun, temperature of the water, it will absorb some radiation and the temperature of the water also will increase. This case can be considered as a heat generation. The heat generation is a volumetric phenomenon. In other words, we have heat generation inside the volume of the medium or object, and for that reason, the amount of the heat generation is, or the unit for the heat generation is watt per meter cubed. So we know how much in terms of watts of the energy or heat or thermal energy is generated in the how much volume of the object. For that reason, EDA generated or rate of heat generation for an object is equal to integration over the volume of that object, EDA gen, which is the specific heat generation, time differential of V, which shows the volume element of the medium. So simply, if we integrate, we can find the equation that then this is volume uh, of the object which we are going to find or calculate heat generation for that object. For example, if it is cylinder or if it is a sphere, we need to calculate the volume of that, and EDA generated is a value which we can calculate it by different methods. For example, if it is wire, we need to have, that we can find the volume of that wire, and also we need to have current and resistance of the wire. Then we can calculate the EDA generated times V will be the total heat which is generated, the rate of heat generation for that wire. The other example is the heating coils for the for electric oven, for example, which uh, due to this phenomena, which I have already explained to you, we have the heat generation inside that coils, and we need to consider that as. So up to here was just some introduction for us to start to develop one-dimensional heat conduction equation. Up to here, you have seen the what is heat transfer. It is a vector. The direction is important. We have seen three different coordinate systems. We have seen the Fourier law, with the main equation which we have for the heat conduction, and also we have seen transient and also the steady heat transfer. And finally, we know that when we are calculating heat transfer by conduction, especially, we need to also consider the heat generation or rate of heat generation. And why here we are going to develop one-dimensional heat conduction, and why we start with one-dimensional? Because most of the real problem or real heat transfer problems, like what I told you, from the window, from the plane wall, from the even the cylinder, from the from spheres, for example, can be considered as one-dimensional heat conduction or heat transfer problems. So first, we will start with one-dimensional equation. Then we can, develop them for the three-dimensional. For one-dimensional heat conduction equation, we will develop the equation, this equation, in those three different coordinate systems: rectangular, cylindrical, and spherical. And here you will see why we are going to use these three coordinate system, because it will simplify our calculation, and you will see in our in the process of the development of this one-dimensional heat conduction equation. Okay, so let's see how we can find the heat transfer, or how we can develop the equation to define or to calculate heat transfer through a large plane wall, like what you can see here. Actually, this is an element which we have selected, and as we mentioned here, it is a large plane wall. Here we can consider that the heat transfer is in this direction. However, here we use a rectangular coordinate system. Then we have three direction: x, y, and z. But we can deal with it as just one dimensional heat transfer, or we can calculate the heat transfer in only one direction, because it is a large wall. So the heat transfer in this direction is only important for us. So we select an element like what you can see here. The element, we call that, for example, x here, which is a volume element. Then if we write the heat balance equation actually for this volume element, we have rate of heat by conduction to this volume element from this direction. We select our reference here. This is the x, the distance from our reference. This is x plus delta x for our element. So the thickness actually is delta x. The thickness is delta x. X here is x, here is x plus delta x. And A is the surface of this volume element which we have selected. Then we have a heat transfer by conduction to this volume element, rate of heat conduction at x, okay, minus, rate of heat conduction at x plus delta x. This is the change in the energy of the for this volume during this heat transfer process. Actually, the energy at this point minus energy at this point. This amount of energy come to the system by conduction. This amount of the energy will go out from our volume element. So rate of heat conduction at x minus rate of conduction at x plus delta x. The direction here is important. This is to our volume. This is from. This is going out from our volume element. Plus rate of heat generation inside the element. uh, we assume that we have heat generation inside the volume element. You know, this is the special case which we just assume that we have also heat generation inside our element. All of this will be equal to rate of change of the energy content of the element. In other words, these all of these equation is the energy balance for our volume element. Energy for this volume element only is changing due to the heat which is come to the system or goes out from the system or is generated in our volume. So we write rate of heat conduction at X as Q dot X, rate of heat conduction at X plus delta X as Q dot X plus delta X, and the rate of heat which is generated inside our volume element is E dot generated. This is totally will be equal to the delta E of element, change of the energy content of the element per delta T or per time, which will be the rate of change of energy content of the element total. Now let's see how we can find each one of these terms actually. Delta E of the element totally means the, with time, because we are talking about the rate here, it means the energy content of the element will change with time. In other words, if the initial time is t and the final time is t plus delta t, in other words, in delta t of interval, for example, delta t is 1 second, then the energy of the system at second 1 minus energy of the this volume element at second 0, for example, if t is equal to 0 and delta t is equal to 1 second, for example. Then the change of the energy will be equal to E, the energy at this time minus energy at this time, which you know that we can use this equation because here we have only conduction. We can write mc delta t, t as temperature upper t, mc t at t plus delta t minus t on upper t down lower t. MC, this is MCT, MC delta T. Heat transfer by the total heat transfer actually. And M, which you see here, is the heat capacity of the element, and M is the mass of our volume element. Here we don't have mass, but we have volume, so we can calculate by density and the volume. A delta X is the volume of our element. This is our element. This is delta X. This is surface area. So the area times the thickness will give us the volume of this element. And rho is the density. Rho is equal to M by V. So here M will be rho V. Rho, we have density of the substance or the medium. V is A times delta X. Simply we substitute here T. This is the temperature difference for these 2 points, X and delta X. How about the heat which is generated inside the wall? If you remember, we had this general equation which says the amount of the heat which is generated inside the wall, or rate of the heat generation inside the wall, times the volume of the element. It is generated, for example, if it is a wire, for example, or any reason, any other reason for generation of the energy which we can calculate here, we need to multiply by the volume of the element, which is A delta X. So we have delta E of the element, we have rate of heat generation inside the element. We substitute these two in this equation, and we can get this Q dot X here minus Q dot X plus delta X we have here. We substitute this in this equation, and rho, see, this is delta E of element. We have calculated here. We substitute this in this equation, and finally our equation will be this rho c a delta x from this t minus t plus delta t minus t lower t divided by delta t. This is come from equation. So simply we substitute 1 and 2 in these 2, 6 equation, and we can get this equation. Now we divide both sides of this equation by a delta t delta x, or the volume of the element. The left side will become negative 1 by a q dot x plus delta x minus q dot x. If you notice, we have the change or restructure our equation, and we put this negative sign here. If you notice, q dot x is shifted with q dot x plus delta x divided by delta x a delta x. This term divided by a delta x. This term divided by a delta x, it will remain only dot generated. The right side divided by a dot delta x, this term will be removed. So we have rho c t upper t down t plus delta t minus t, or upper t down lower t, by delta t, which is or the change of the time interval. Now in the next step, we assume that, or we take the limit of both sides of this equation when delta x approach to 0 and delta t approach to 0. In other words, for a very small thickness and very small interval of the time, we are going to see how will be this equation 1 divided by a, and from the differential equation that it will be the actually the definition of this equation when delta x approach to 0 here, when delta t approach to 0, will be the partial equation actually. So 1 divided by a partial of q dot x plus delta x, q dot x by delta x actually. However, here if you notice, we have substituted, I will come back to this. So 1 by a, and this one I will come back, e dot generated equal to rho c, rho density and partial of temperature by with respect to time. This is limit of t plus delta t plus t divided by delta t when delta t approach 0. If you remember from the mathematics, this means rho t by rho t. So this term will become this. And how about this side? This side will be like this. Limit q dot x plus delta x minus q dot x by delta x when delta x approach to 0. This one also become this partial of q dot with respect to x. We can substitute this here, but if you remember, for q dot, we have Fourier law equation, so we write the partial of negative k, partial of t with respect to x, totally with respect to x again. So 1 by I partial of this term with respect to x. We just substitute this here. I hope it is clear for you. It is just from differential equations, but simply you need to just know that this limit means this, and this limit means this term. Now we have this general equation. Actually, this is the equation which we are looking for. This is the equation which we have developed in the previous slide, and this is a general equation for one-dimensional heat conduction in rectangular coordinate system. K is the thermal conductivity, we assume that if, this is general form, we assume that K or thermal conductivity is variable. We assume usually that the K is constant. For example, we say for the iron, the thermal conductivity is this value. But thermal conductivity is function of the temperature of the object. I think I have already discussed in previous sessions. So here also we assume in general form that all terms which we have here are variable. K is variable, temperature is variable. We have a transient heat transfer phenomenon here, and this is general form. If the thermal conductivity is constant, then the K here can bring out from this equation, and this K, if we are going to reach this one, so this is variable. For variable thermal conductivity, transient heat transfer, and heat generation, we have this variable thermal conductivity with heat generation. We have heat generation, and also we have transient heat transfer. In this special case, for example, our equation is like this. Now we are going to reach this equation when we have transient heat transfer, we have heat generation, but with constant thermal conductivity, or K. In this case, K can bring out from this partial. It will be like this: K rho X rho T, for example, rho X plus E dot J equal to rho C partial T with respect to time. Okay, K here. Then if we divide all of this by K, we will have, this rho multiply the partial multiply, so partial square of temperature is totally power 2. This is divided by K, so K will be removed, plus this E dot generated divided by K equal to rho C divided by K actually. But here we define this thermal diffusivity. It is a property of substance actually. It only depends on the thermal conductivity of the substance, the density of the substance, and the specificity of substance. If we, here we have actually like this, rho C divided by K. Okay, we have like this, but rho C by K, if we write like this, just this side, K, if we can write this, that is 1 divided by K divided by rho C. This K divided by rho C can be, is called alpha or thermal diffusivity. So we substitute here rho, the partial of T with respect to the temperature with respect to the time, like this. So when we have constant conductivity, our equation will be simplified to this one. K is not variable anymore, it is not in this partial. The other special case is when we have a steady state, constant conductivity and a steady state. It means the temperature doesn't change with time. This term will be 0. So the right side will be 0. This equation actually will be simplified like this. We have this, but we have heat generation, we have heat transfer, but we don't have the change out in the temperature with time. Only with the location, the temperature will be different. The other special case is transient but no heat generation. In this case, this term will be 0. We have this transient, so in this case we have this equation. This equation will be simplified like this. This term will be removed. The third special case is when we have a steady state and no heat generation. for this heat transfer problem in the rectangular coordinate system. In this special case, this will be 0, this will be 0, and we have only this, which the partial will become also the differential form, d squared 2, or the second derivative of temperature with respect to the direction, or the direction of the heat transfer will be equal to 0. This is the equation which we will use a lot in future example. So here also is mentioned general, one-dimensional form, and some special cases. No generation, this will be 0. A steady state, this term will be 0. When it is steady and one-dimensional, we have only this term. This is the term which we will use mainly in the problem. For plane wall especially, we will use this equation. Next, we will develop same equations, one-dimensional heat transfer in other coordinate systems. Okay, now let's see how will be the heat conduction through a long cylinder. Imagine we have a long cylinder like this. Its length, is L, for example, or infinitive long actually. But we select elements like what you can see here. Of that, the element which you can see here, again similar to what we have done for the plane wall. Here again we need to select a volume element for this long cylinder. We select our volume element like this. You can see with this thickness, it's delta R, and its length is L. The length of this cylinder is higher than this, but our volume element length is L actually. And now this is a cylinder, so we have temperature difference between the two surface of the element which we have selected. We select the coordinate system for this problem. What is the appropriate actually the coordinate system for this problem? For sure, the cylindrical coordinate system will be the most appropriate coordinate system which we can select for this problem. So we select our coordinate system like this, the cylindrical coordinate system, the center of this cylinder as our reference, and we have R like this. Why this problem is one-dimensional heat transfer or one-dimensional heat conduction actually? Because if you notice, for this cylinder or line cylinder actually, as we discussed earlier, temperature in the length of the cylinder will remain constant. So usually we don't have heat transfer in this direction, and heat transfer is from the center of the cylinder toward its surface, or in R direction. So here again we have one-dimensional heat conduction problem. We don't say here heat transfer by conduction, we just say heat conduction, which means heat transfer here is only by conduction. So we select our element like this. Its inner radius is R, its outer radius is R plus delta R. In other words, the thickness of the element is delta R. We assume we have heat generation inside our volume element, heat that generated. And we also assume we have heat transfer through this due to the heat transfer. Now again, if we write the heat balance or energy balance equation actually for our element, we will have like this. Rate of heat conduction at R at this point minus rate of heat conduction at R plus delta R. In other words, this dash line is our element. So hold this dash line from here is our element. So to its inner surface, we have heat conduction through our element. From this surface at R plus delta R, we have the energy is going out from our element, so it is negative rate of heat conduction at R plus delta R. We have heat generation inside our element. We assume we have. It is positive because it will create heat or thermal energy inside our element. Totally, these are the energy which come to the element or goes out from the element, or it is generated inside the element. These whole changes of the energy will be equal to the rate of change of the energy content of the element, similar to what we had for the plane wall and the rectangular coordinate system. Again, rate of heat conduction at R, Q dot R. The rate of heat conduction at R plus delta R is Q dot R plus delta R. And here is the rate of heat generation inside the element, delta E of the element by delta T, or the time duration, time interval. Again, similar to what we have for the plane wall, delta E of element, we can calculate ET plus delta T minus ET. You know the reason why we have these two. The difference here is only the volume. Here, A delta R is the volume of our element. A is the surface area of it times its length. So A delta R is the volume of our element. And E dot generated inside our element is equal to the rate of generation specific times the volume of the element. This is volume of our element. Then if we substitute this delta E element, this equation for E dot generated of the element, this equation in the, these two, 1, 2, in this equation, in the equation A, 1, 2 in equation A will give us this. Q dot, same Q dot R plus delta R, same E dot generated instead of this, we rewrite this. And here also, instead of this delta E element, we write this divided by delta T. Again, we divide both sides of this equation by A, by A delta R actually, or the volume of our element. And here we restructure our equation, add this negative sign here. And our equation will be simplified like this. Divide by, divide by 1, or divide by actually A delta R, like this. So this is divided by delta R, the whole both sides of this equation. We will have finally this equation. Now, similarly, like we have done before, we take limits of both sides of this equation when delta R approach to 0, and the right side when limit of this when delta T approach to 0. Again, delta actually limit of this here when delta R approach 0, here when delta T approach 0. And from mathematics, from the differential equations, we know that the limit of this term when delta T approach to 0 means rho T, or the partial of temperature with respect to time. And same here, with same procedure like plane wall, we can find this equation. Again here, I have written how we can reach this equation by the limit which we get for this. Limit Q dot R, R plus delta R, Q dot R divided by delta R when delta R approach to 0 is equal to partial of Q dot. This is based on definition. This is from mathematics. We know this. Partial of Q dot by with respect to R, and Q dot we know from Fourier's law. We just substitute here that equation. So again, this is our main equation. In cylindrical coordinate system. For variable conductivity, that equation can be used. K is inside this partial differential. And when we have constant conductivity, similar to what I have told you in previous slides for the plane wall, K will become, we can bring out K from this partial, and if we divide both sides, I'll hold this equation by K, it will be reformed like this. Again, you can see alpha, if you remember, alpha, K divided by rho C. And similarly, like rectangular, here also when we have a steady state heat transfer, this term will be 0. This term will be 0, so the whole right side will be 0. Then our equation will become like this. Here is constant thermal conductivity, and here also I think better to write constant K. Then so a steady state and constant K, our equation will be this in cylindrical coordinate system. When we don't have any heat generation, this equation will become this term will be 0 actually, or this term better I can say. Here also constant K. When we have a steady state, in other words, this term 0, and no heat generation, this term also 0, then our equation will be this. It will change to differential form, differential derivative of R dt by dr totally by dr. This is our general equation when we have a steady state, no heat generation. This is the main equation which we usually use. However, the general equation is this one. It can be simplified to each one of them based on the specific problem which we are dealing with. So the form that is ready to integrate. This is important, and its equivalent the alternative form is this one. You will see why these two important. Because these are the differential equation. How we can solve them? By this equation we can find temperature at each point of this cylinder, for example. By this equation, we can find temperature at each point of the plane wall. Up to here, we have just developed the equation in these two coordinate systems. Next, we will develop the equation for the spherical system with, with same procedure. I'm not going to go to the detail of that. With same procedure, if we write the heat balance or thermal energy balance for our element, assume we have an element, we have a sphere, okay, then we are interested to see how is heat transfer through that. Again, we select, here is a sphere, we select a shell, a volume element. In that sphere, we select the center of the sphere as our reference, at the, again here, the heat transfer is one-dimensional. Why? Because heat transfer in R direction from the center toward the surface. So again, we have one-dimensional heat transfer or one-dimensional heat conduction. Now we are going to develop the equation for heat conduction for a sphere. If we select the spherical coordinate system, our calculation will be much easier because we are just dealing with R, the one direction only. So we select our element like this, at R is its inner surface, R plus delta R is its outer radius, and so its thickness actually is delta R. Again, if we write the energy balance for our element, if we go through all of these, finally we will reach this equation for heat transfer in this sphere. 1 divided by R2 partial of these totally with respect to R or radius. If you notice here, heat transfer is a function of R or the radius, or which shows the place of the which uh, heat transfer or the temperature we are interested to know about that. Heat generation inside the element or whole sphere actually here, this is general equation, and the density and specific heat, and also the time. Now, similarly, what we had for the for the plane one and also for the cylindrical coordinate system, here we have some special cases. If k is constant, we can bring it out for all this equation divided by k, then substitute the k by rho c as alpha, then this is our equation in a spherical coordinate system for heat transfer when k is constant. As the other special cases, I think you already can guess how it can be. A steady state, this term will be zero. So our equation will be like a steady state and constant thermal conductivity. When we have transient but no heat generation, this then this is we have this, but this term will be zero. When we have a steady state and no heat generation, it means this zero. So this is our equation, which can be restructured or rewrite like this, and this is our equation actually. This is the equation which is ready to be solved or to be integrated. Later, in next session, actually, you will see some examples, and you will see how we can find or solve these differential equations. Now, up to here, we have just developed equations. So you have seen how we can develop these one-dimensional heat conduction equation in those three coordinate systems. Next, we will see how we can extrapolate these for multi-dimensional heat transfer or heat conduction. An interesting property of the developed equation for the three different coordinate system for the one-dimensional heat conduction actually is we can check also this equation and we can show the developed general equation in each one of these coordinate system in a compact form like what you can see here. This is a compact form. This is a general form of the equation for those three for one dimensional heat conduction in the three different coordinate system. Simply in this equation, we have n. If we substitute n by 0 or 1 or 2, we can reach the developed equation which you have already seen in previous slide. So if n is equal to 0, if we put n0 here in this equation, we can find we will reach this equation, which is the one-dimensional heat conduction equation for plane wall. If we put n equal to 1, then we will reach this equation, which is a one-dimensional heat conduction equation for in the cylindrical or for a in the cylindrical coordinate system, or actually for a cylinder. And is equal to 2, if we put n equal to 2, we will reach this equation, which is the heat conduction equation for a sphere in a spherical coordinate system actually. When we use n equal to 0 actually, we need to substitute r equal to x. Instead of r here, we write x because it is in a rectangular coordinate system. Simply, if you just know this equation, if we just memorize this equation actually, and if you know for each one of the plane wall, cylinder, and sphere, you need to put which one of these numbers for n, and you can use this equation for all of those shapes or geometries. And also this equation is similarly like what we have seen in for each one of these objects or geometries can be simplified based on the specific heat transfer condition. No heat generation, this term 0. Steady state, no transient, this term 0. And constant thermal conductivity, this can bring out, and so on. So if you just memorize this equation and know this, and you can use this equation for one-dimensional heat conduction for these three specific or special geometries or coordinate systems. You have seen how we can develop a one-dimensional heat conduction equation. Now let's see how we can develop general heat conduction equation. However, as I said before, the one-dimensional heat conduction equation are usually enough to solve heat transfer problems, but it is also useful to know how we can develop general heat conduction equation. In some special cases, we may not be able to ignore heat transfer in other two directions, and we may have two-dimensional or three-dimensional heat transfer, which we call them multi-dimensional heat transfer. In this section, you will see how we can develop this equation. Similarly, the procedure is same, only the equations will include more components and will be more complicated. And mainly you need to know about the one-dimensional heat conduction equation. This information, which is about the multi-dimensional heat transfer, is just something extra for you to know how you can develop these equations for a general situation. We have multi-dimensional heat transfer or heat conduction actually. So in this case, imagine we have a three-dimensional heat conduction through rectangular volume element. We select, in plane wall, if you remember, we have just in one direction heat transfer. Here we select our element like this. It is volume element, and we assume that we have heat transfer in x, y, z direction. Again, we write this equation, the energy balance for our element, but this time we have three directions. So q dot x, q dot y, q dot z, the rate of heat conduction at x, y, z. And everything is repeated. Q dot x, q dot x, the plus delta x, if you remember. Here, q dot y, q dot z is added to our equation. So equation is bigger and more component is added to our equation. Again, delta I of element is that generated of the element, we substitute, and it is simply like before. We substitute delta I of element is that generated of the element in this equation. Our equation will be simplified like this. Then if we divide the both sides of this equation by delta x, delta y, and delta z, which is again here is the volume of our object actually. So this equation will become this one with same procedure like what we had for the one-dimensional heat transfer. Now, if we again use the limit and take limit of this side when delta t approach 0, and this side, but this time we need to assume that ax, actually ay and az are approach to 0, or here delta x approach to 0 for this term. Limit delta x approach to 0 here. Limit for this one, delta y approach to 0 for this one. Limit delta z approach to 0. This one will be rho q dot z by rho z actually. And q dot again ka, it will be equal to the, by Fourier law again we can write it And finally, this is the general equation for the uh, three-dimensional transfer uh, mm, or three-dimensional transfer in a rectangular coordinate system. You can see, if it can be simplified to one-dimensional transfer equation. Actually, if we don't have these terms, then it just becomes this, which is one-dimensional transfer. So you can see how we can develop this equation. When if thermal conductivity is constant, again, it will become like this. And that equation, the general equation, can be simplified for a steady state, which we have a specific name for that, Poisson equation. And when we have transient heat transfer but no heat generation, the equation, this term will be removed. And the equation will just be like this. We call that diffusion equation. And when we have a steady state and no heat generation, then our equation will become like this. This is the very general equation. We call that Laplace equation, the general form of the multidimensional heat transfer or heat conduction equation, actually ready for integration. As I said, for third subject, we will just focus on one-dimensional heat conduction. In cylindrical coordinate system, again, simply we select our element like this. We need to write the uh, energy balance equation for our element, and if we go through all those processes to write Q dot to the uh, our element Q dot, which go out from our element heat generation in the element, and so on, we can reach this equation. Or the easiest way, we can write like this. We have this equation, okay? And if we just go from the rectangular coordinate system to cylindrical coordinate system, simply we need to substitute x by r cosine of phi, y equal to r sine of phi, and z equal to z. If we substitute these three in this equation, we will reach this. This is the general form. Cylindrical coordinate means multi-dimensional heat conduction. A spherical coordinate system, in this general equation, in this one, 238, we, instead of x, instead of y, instead of z, we need to substitute these three. X r cosine phi sine theta, y is equal to r sine theta, sine phi, sine theta, and instead of z, we need to write cosine theta. If we substitute all of these three in that equation, we will reach this equation. Very long equation, which actually is not out of the content for this chapter. This is just extra information for you, which we can have, or which we can develop this equation for three-dimensional heat transfer as well. In next session, we will discuss about how we can solve the equation for how we can solve these equations actually for one-dimensional heat conduction, real examples, and actually how we can integrate these differential equations. We'll see about that in next session. Thank you so much for watching this lecture.